In this tutorial, we're going to give a geology overview of the background information that you need to know in order to operate the Tsunamibayes program sufficiently and to understand both the inputs and outputs that go into that as we do this simulation of tsunamis. In this video, we're going to specifically talk about how do tsunamis occur, hopefully build a little bit more intuition about the geological processes that cause those things, specifically for people that don't have that much of a background. Then we're going to describe how geologists will talk about earthquake ruptures. We'll go into a bit of the terminology that's used there. And then finally, we'll give you an introduction to the modeling assumptions and simplifications that we're going to make, specifically in conjunctions with Geoclaw, as we eventually move towards simulating the actual waves emanating from these earthquake events.
We're now going to go into a brief overview of tsunamis, the geological processes that cause those waves to occur. This is mainly geared towards and meant for people that are much more on the math side and don't have as much of the geology background. For people with geology background, this will be very, very familiar to you. Feel free to skip it if you like. So, as you probably know, the Earth is made up of these tectonic plates, and those interactions between these plates are very, very complex, just based on the geometry, the orientation of how those are going to interact. Some are splitting apart, some are converging upon one another. And so we'll see later on, as we are trying to model these faults, we're going to have to make several simplifications. But it's important for us to understand kind of those interactions so we can make educated simplifications that are there. Again, these interactions based on the geometry, there's many possible orientations we can have for this fault interface. We have strike-slip faults, which are sliding past each other, like as shown here. We have thrust faults that are kind of pushing up against each other at shallow angle, and different names for faults that are, again, kind of converging on one another based off different orientations. We have some nomenclature for how we describe kind of these two faults coming together. We have the footwall and the hanging wall. The footwall kind of being the base, and the hanging wall being kind of sliding up and down that interface. We have this fault plane here, and this is going to become very important because this fault plane, the geometry, that is going to be one of the ways that we are going to describe that fault interface. It is very, very important as we talk about modeling the deformation that occurs when an earthquake happens. So we're going to go now into some videos that explain a little bit more of the processes going on here. I think they show this very, very well, provide a lot of good intuition.
Subduction zone megathrust earthquakes, the most powerful earthquakes, can produce tsunamis through a variety of structures that are missed by simple models. The basic model shows rock above the convergent plate boundary being compressed and bent as it stores elastic energy. Once friction is overcome, the overriding plate slides abruptly up the fault, causing the leading edge to heave seawater upward, generating a tsunami. This shallow angle reverse fault is called a thrust fault because the overlying plate thrusts up over the subducting plate. Let's explore different tsunami-producing mechanisms by examining three famous earthquakes. In 2011, the magnitude 9 Japan earthquake ruptured a fault area 500 kilometers long by 200 kilometers wide, over an interval of nearly 3 minutes. Surveys of seafloor bathymetry before and after the earthquake document up to 50 meters of fault displacement at the Japan Trench. What would that look like in cross-section? During the rupture process, the overriding plate slid up the west-dipping fault plane. That uplifted the seafloor by 10 meters, producing the local tsunami that rushed on shore within 20 minutes of the earthquake, and the distant tsunami that spread over the Pacific Ocean basin.
One really quick thing here that I'll point out is they mentioned that this rupture happens over a decent chunk of time. Here it said for this one it was about 3 minutes. Later on we'll see that as we model this using Geoclaw, we're going to make the simplifying assumption that this seafloor deformation happens instantaneously. And honestly, for our purposes, that works just fine. We're going to look at another event here that they describe just for the sake of showing that, hey, we have different types of earthquake ruptures that can occur and still cause a tsunami.
How deformation, as well as fault displacement of the overriding plate, can produce a tsunami. The 2010 magnitude 8.8 Chile earthquake tore a rupture zone 600 kilometers long by 130 kilometers wide. Although the rupture began at approximately the same distance from the trench, there was little to no displacement at the trench as there was during the Japan earthquake. So, what generated the local tsunami that resulted in 123 deaths and produced major damage in coastal towns? Fault displacement ranged from 5 meters at the hypocenter beneath the coast to 10 meters midway to the trench, then decreased to little or no displacement at the trench. Westward displacement of the continental shelf above the plate boundary caused broad uplift of the seafloor. In addition, the change in amount of displacement along the plate boundary caused internal deformation of the overriding plate. These effects combined to uplift the ocean floor by 2 to 3 meters. This sudden uplift generated the deadly local tsunami along the coast of South America and Juan Fernandez Islands. Alerted by strong ground.
Alrighty, so the big takeaways here that I think are just really essential is understanding that it is this vertical uplift that is caused by the earthquake that generates the tsunami. We talked about how there are strike slip faults that are just sliding past one another, and those usually are not going to cause tsunamis because we have no seafloor deformation. We have no big displacement of water that occurs from that. That's, I think, one of the biggest takeaways to take from this. We'll move on to this next visualization of tsunamis as well that bring up another couple great points. Again, hoping that this adds some intuition. Once again, we're talking about a sudden rise or fall in the Earth's crust that causes the water above it to rise or fall. That is a tsunami. So here's another visualization. We see the pressure building up in this thing here, this instantaneous deformation, and the wave that now propagates from that. Probably the most important thing I'd like you to take out of this is realize that when that deformation occurs and the wave is generated, again, the wave is going to be pushed out in both directions relative to that fault line. And in one direction, we're going to get that the crest of the wave, or the bottom, the top portion of that wave, the highest point, is going to be the first part of that wave that's going to arrive as it propagates farther and farther out. We have another side of the wave where it's the trough, or the bottom part of the wave, that is going to occur. The crest first wave, that's what we call a positive wave. That's kind of this big wall of water that we imagine. The negative wave is where we're going to see that the water is going to recede before the big wave comes. And we'll see a couple examples of that as we go. We'll also see here that in the deep ocean, the amplitude of these waves are very, very small, nearly imperceptible, but they travel also very, very quickly. As those waves travel inland, its speed is going to slow down as it meets some more resistance, but the amplitude of that wave is going to now increase quite a bit. And as it starts to make landfall, we're going to see here that in this case, it is the positive wave arriving first. We see that wall of water coming, rushing into the coastline. But you notice here that after it inundates that coast and that part of the country there, now we get this negative wave of the water receding. An important thing to remember with tsunamis is multiple waves are going to be arriving and receding as it goes through here. So it's not just one wave of water. We're going to go through this pattern of this kind of push and pull of waves until that wave dies out. So in this last video here, we're just going to see another quick visualization of this tsunami here. Again, the hope is that this is building a lot of good intuition. So we have this huge chunk of earth that's being displaced. So this is a lot of water that is being jutted out. Again, we start shallow, but as we start moving towards the coast, the wave is going to get larger and larger, but also move smaller and smaller. So in this example, we're actually seeing that the negative wave is first out of the bay, and then we have the positive wave of the tsunami. So that's going to be important as we look at observations of different tsunamis, of people recounting time negative wave occurred versus a positive wave came. That's just important to know that those two types of waves are here. We're also going to see that there are multiple waves happening here, and it's not necessarily the first wave that is necessarily the max water here, especially in the case that the negative wave is the first to arrive.
Now that we understand a little bit more about tsunamis, the mechanisms that cause that, we're going to dive a bit deeper into some geology terminology that describes earthquake ruptures, how geologists will represent seismic events. That will really serve as a foundation as we get into understanding how are we going to model those earthquakes in our tsunami simulation. And it also serves as a foundation for us to understand, because we need information about that fault in order to run these simulations and to gather this information. And we'll be able to understand a bit better about how we get that, where that comes from. So first of all, let's return to kind of this image here. We looked at all the site profile as we watched kind of videos about how tsunamis are formed. And essentially what we'll learn is that we're going to talk a lot about the geometry of this interface here, because that geometry has a large effect on the deformation that occurs and that causes that tsunami wave. The angles, the orientation, the amount of displacement that you'll get between those faults all contribute to describe that earthquake rupture. You'll kind of see on this image on the right as well how this earthquake rupture doesn't just occur in one small point, but it occurs along an entire length and width of area where either the seafloor or sometimes even above ground, we get deformation that occurs as those two faults move past one another and push up against one another. So let's dive into kind of some of these geological terms. Here is a diagram. I am not a huge fan of this because we put all these terms in one place and it's kind of confusing if we don't know what's going on. But we're going to break this down bit by bit to understand what these angles are talking about, why that's important. First and foremost, though, let's clarify that all these terms that we're going to be talking about when we're describing this earthquake, these faults, we are talking about what we call the fault plane. So this is kind of this imaginary two-dimensional surface that is the interface between those two plates that are coming together. So we have the fault plane, we have something called the fault trace, which is just kind of, or in other words, kind of the fault line, which is kind of that line on the surface where those make contact. And we'll see later on also we have some terminology of what we call the footwall and the hanging wall here. As we have two plates coming together, that's going to help us describe that geometry. So let's start with kind of some of the basic ones that you're probably familiar with. So we talk about the length and the width of the fault plane. That is kind of in reference to the length and width of the rupture zone here. Essentially, yeah, like how long is that section of that plate boundary that is breaking and moving past after pressure has built up. We're also going to talk about the latitude and longitude of the centroid of that fault plane. In other words, this is what we also call the epicenter, which is kind of the point on the surface where the earthquake or seismic event is emanating from. And we talk about the depth. And this has reference kind of to the hypocenter of the actual earthquake. So we talk about kind of latitude, longitude, kind of this 2D on the surface of the globe. Where is that earthquake happening? But the reality is the location where those plates are moving past each other, where that pressure is built up, is well below the Earth's crust. Add those plates, for example, in a convergent zone where those plates have built up pressure underneath the Earth's surface. So the distance between the epicenter on the surface and the actual point of the earthquake below the surface is what we call the depth. Here, kind of the definition I use is depth of the specified point below the seafloor. So again, this is referencing where the earthquake is emanating from below the seafloor. Now we're going to get into some more of the complicated terms that you may not have heard of before, and a lot of these are describing the angle, the angles, the orientation of that fault plane. We're going to use some images here. Hopefully this is going to make more sense as we go through some examples. But the great thing is you can also look online. They have a lot of really good explanations, images, diagrams of how this all works out. I'm taking kind of these definitions from Geoclaw's ClawPack documentation. This is what we're going to be using later on in our modeling. So for the sake of consistency, I'm going to rely on their definitions here, and we're going to break down some of these more complicated parts. We get back to this diagram. The first thing that we're going to start with is we're going to talk about what the dip angle is. And when we talk about dip, this is the angle at which that fault plane dips downward from the top edge. And it's an angle that we are essentially bounding between 0 and 90 degrees. So kind of in our big diagram here, when we're talking about the top edge, we're talking about this guy here. So we got our fault plane right there, and we're talking about the top edge here. And the dip is essentially, hey, if we have that surface there, what is the angle that I'm dipping down, what is the angle that that interface is dipping down as it's pushing into the earth or even sliding past things there. So let's look at maybe a couple more clear examples with this guy. I like this image because I think it shows it really, really well. We have kind of this protrusion of this rock face, which is on this fault. And again, we can kind of see that we have the edge of our fault plane here, and we're trying to describe what's the angle. Is that really steeply going into the earth? Is it really shallow? That's what we're trying to get at when we're talking about dip. And again, we constrain it between 0 and 90 degrees because we're not going to talk about a dip that's coming backwards on us here. If we look back on image a couple of guys back, we're not describing. We are describing the angle of the footwall, as you can see here. So this angle right here. We are not describing this angle, which is going to be more than 90 degrees back from that surface there. So that's just an important clarification to help things kind of just stay in our mind here. Now we're going to move on and we're going to talk about strike. Again, this one I think doesn't make sense to me. We got strike right here. We're going to explain a bit better what that actually means. So when we talk about strike, we're talking about the orientation of the top edge of a fault plane, measured in degrees clockwise from north. So again, when we say top edge, this is what we're talking about here. So we have these faults going into the earth here. We can see the dip that's labeled off here to both to the right and to the left. And we have both of these guys kind of running up and down. And again, we're measuring this in degrees clockwise from north. And there's a clarification that we have to do here. So let's define kind of our coordinate system. Let's say that we have north to south running here, which means we have east to west moving there. I think I got that right. Alrighty. So according to this coordinate system, both these faults are running north to south. But the interesting thing is when we're talking about strike, that angle can be anywhere between 0 and 360. So the question that kind of comes to mind for me is, hey, are these two faults, do we say that's 0 degrees strike? Or do we say that's 180 degrees strike? How do we constrain that? And the way that we do that, the second sentence says the fault plane dips downward to the right, moving along the top edge in the strike direction. To me, that doesn't make a whole lot of sense, but we use something that we call the right hand rule, and hopefully after going through this, that phrase will make a bit more sense. And the way we kind of define our orientations here is if you put your hand down in the direction of the dip, your right thumb is going to point to the angle of the strike. So let's look here on this left example. So if my fingers on my right hand are pointing down here, my thumb is forced to point down here, and we'll see that's pointing towards the south. So for this left guy, this has a strike of 180 degrees. If we look at this right guy here, and I put my fingers down towards the direction of the dip, so again, it's like I'm putting my hand on that fault plane. In this case, my thumb is going to be pointing up or towards the north. So this one, we're going to call it a 0 degree strike. Again, 0 and 180, these are simple examples, but these could be at any angle relative to north. But we're still going to use the same convention, the same right-hand rule to define that. So those are two of the angles that we have that describe those things there. We need to talk about, and I really like this diagram because, again, I think it just shows very clearly, okay, hey, here's north. This is the angle between that and that top edge there. We still do have a couple more terms and one more angle to get ourselves oriented in 3D space here. And the one we're going to talk about is rake. And rake, again, we'll read this definition, we'll break it down, is the angle that the fault plane, in the fault plane in which the slip occurs, measured in degrees counterclockwise from the strike direction, between -180 and 180. Okay, so let's get our orientations right here. So we're measuring rake relative to the angle of this guy here. But what is rake? Let's try to visualize that a little bit. So again, let's remember that we have these two plates that are sliding past one another. But they can slide past one another at any orientation. We can have them coming head on. They could be askew, slightly like this. They could be moving side to side. So this is kind of the term that is going to help us constrain how are those faults moving relative to one another. I really like this diagram here because you can see the scratch marks that the faults have left as they've been sliding past each other. On this example on the right, you can kind of see that the orientation of those scratch marks is very much left to right, which kind of implies that those plates are moving past each other in kind of this side-to-side motion here. Conversely, on these other two images here, you can see that these scratch marks are nearly vertical. These ones are slightly angled here. And you can see kind of this is the geologist marking out these angles. And this implies that that in this case where the markings are more vertical, this implies that the faults themselves are sliding up and down like this. So in the first one, the scratches were kind of side to side. It's like the faults are moving side to side like this. And this one of the scratch marks are vertical. It's like we have that foot wall and that hanging wall that is sliding down and just scraping the rock as it's coming down. If that's not clear yet, here is a really great just breakdown of this in its most simplest form. Just note for a strike slip earthquake, rake is near 0 or 180 degrees. For a subduction earthquake, the rake is usually closer to 90 degrees. This is the exact same effect that we've been talking about here. Is again, when we're sliding past each other like this, and the plates aren't converging, that's either a 0 or 180 degree rake direction. When the plates are coming together like this, they're perpendicular. That's what we call a 90-degree rake. Hopefully that makes a little bit more sense. The last one that we'll talk about to tie everything together here is now the slip. The best way that I like to look at this is the slip is the distance the hanging block moves relative to the foot block. So again, remember that terminology there. We got this foot block is this top guy, this hanging wall or hanging block is down to the right here. And we're looking at what is the actual displacement, the distance that those plates are moving relative to one another. This is a very important term because it is highly associated with kind of the magnitude of the earthquake. Essentially, how much did we move? How big was that rupture there? And the way that we define this is we look at the direction that those plates have slid past each other. So again, imagine that this hanging wall originally used to meet up perfectly. This corner was with this corner was with this corner. But when the earthquake happened and that pressure built up and it slipped, we see that it scratched the rock here. And that angle, relative to this top edge here, that angle is what we call the rake. And I really like the way that this vector kind of breaks things down here. So we talk about the strike slip and the dip slip. And to me, this makes it super clear because we're talking about, okay, how much did I move along the same direction as the strike or that top edge there? And then how much did I slide down towards the dip, kind of vertically down? But of course, as this earthquake happened, the fault didn't just go to the left and then down. No, it took kind of the vectorized version of that. So when we combine kind of this left and right displacement here and this up and down vertical displacement, we get what we call the slip vector, which describes the total displacement that we moved in the direction of the rake. This angle here is a little inconsistent. Again, we're defining the rake as the angle from this top edge. So I would actually interchange those there. Of rake is this angle that we slid down there. And again, you can think of this like, hey, if these plates are just moving side to side in what we call kind of the if they're moving side to side in a fault configuration that we call a strike slip fault, you'll see that the slip, the displacement of those faults is directly in line with that strike angle. You can think of here that, hey, when this angle, again, I apologize for the kind of the mix up of terminology, but when we look at this angle from this top edge When we go to 90 degrees rake, so ignore those. Again, this angle from the top edge, that's what we call rake. The degree rake. When we go to 90, that's meaning that we have kind of that foot wall, that hanging wall, they're moving totally perpendicular to one another and scratching, making those vertical marks. So hopefully that makes a lot of this terminology a bit clearer. Again, at first this does look a bit overwhelming, but we've hit all these, and all this is really just to help us constrain, okay, what does the movement of these faults look like? In what direction does it happen? Again, if we look back at this very beginning here, if we want to understand how the movement of these plates causes this wave, we need to know, again, if this is happening at a very steep angle and the slip, that displacement is huge, you can see how we're going to get a much larger wave here. You can see that based off the orientation of that can change how that seafloor is deformed. So that's why it is very, very important. We'll talk about this a lot more as we get into the modeling. But another reason why geologists care so much about all these geometrical things, defining these interfaces between faults, these fault planes, is encapsulated in something called fault plane solutions. So nowadays there are essentially seismic instruments all over the globe, and whenever an earthquake occurs, whenever these waves of the earth moving emanate out, we're able to pinpoint the location of that earthquake because of the angles that we'll notice with that. We'll be able to keep track of, hey, where do we see along the earth that we saw a compression? Where did we see that things stretched in the earth's crust? And with that, we can nail down the locations of earthquakes. But at the same time, we can also learn, as we get seismic data, we can learn about the actual geometry of that fault interface just from instrumentation and understanding which waves are arriving. I'll attach some more videos to here because this can get a little bit complex, and there are some awesome resources that explain this really clearly if you're interested. But again, kind of on the surface, what we need to take away is that understanding this geometry is both important for us to understand how the tsunamis are occurring, how to model them, but also this geometry and paired with seismic data is what provides us a picture, even if we don't know it perfectly, a picture of what those fault interfaces look like around the world. And so when we're talking about the inputs that we're putting into our tsunami-based program, this geometry is affecting the data that we have about those fault planes. We get that from these fault plane solutions. Those fault plane solutions are generated from prior information from past earthquakes on the fault. And when we understand the geometry of the fault interfaces we're working with and studying, that helps us to build in geological constraints. Because eventually what we're going to do is we're going to start modeling tsunamis based off of these parameters, these different angles, amount of displacement of the faults. And if we know that we have a plate boundary that is convergent, where they're meeting perpendicular, and where we have the foot wall and the hanging wall moving relative to one another, that is going to look very, very differently. And we can kind of narrow the things that we're going to sample, because we don't want to be simulating earthquakes that describe strike-slip faults. In fact, strike-slip faults don't cause tsunamis hardly at all. So this helps us to understand faults, helps us to understand, okay, what geometry are we dealing with? And therefore we can model things better. And we'll get into that a lot more next. Okay, now let's talk a little bit more about the assumptions and simplifications that we need to make in order to model these earthquakes adequately. This is going to serve once again as a foundation for later on when we talk a lot more about the processes that Geoclaw is running, understanding all of its inner workings there. And we'll start off by talking about something that we call the Okada Model. The Okada Model is essentially the model that we, as well as Geoclaw, is using to model these earthquake ruptures. And really kind of the elements of the Okada Model state that we're going to use these 9 parameters to define our earthquake rupture. We talked about these earlier, gave definitions. If you're still not familiar with those, feel free to go back and watch those again, because these are going to come up a lot in the code, you're going to see these terms over and over again as we go throughout it. These we kind of treat as 9 independent parameters to describe these ruptures. And eventually we're going to see that there is a relationship between the length of the rupture, the width, and the slip that occurs along that fault line. All those are related to the magnitude of that earthquake event. So later on, when we start sampling and essentially taking different combinations of these parameters to simulate a variety of earthquake events, we're going to take advantage of this relationship to simplify our work. Also, another assumption and simplification that we're going to make along with this Okada model is that we're going to assume that the earthquake event or the deformation that is caused by that rupture is going to occur instantaneously. This is not how earthquakes actually happen in real life. They occur over time. Again, you have different parts of the fault essentially releasing their stress at different times. Think of kind of like a zipper effect, like one epicenter starts it and then it propagates along the length of that fault. We're going to take that complexity out of the equation and essentially just simulate it, hey, all at one moment, this entire portion of the fault is going to deform and slip. Another important assumption that we're making here is that as we're doing these calculations to see, okay, how does the length, width, slip, geometry, angles of this rupture zone, how does that translate to the actual movement of the earth below the ocean floor? In order to kind of be able to compute that, we are going to treat Earth's crust as what we'll call a uniformly elastic material. This is terminology that is used quite often in mechanical engineering when we're talking about materials. But essentially when we talk about a uniformly elastic material, think of, again, every material that we have, metals, even the rock on the ocean floor has some elasticity to it. That is to say, when we apply a stress, it will deform a little bit. Again, even in the case of the Earth's crust, perhaps we don't see that with our eyes, but we're also dealing with extremely large stresses. So based off of stresses, we get deformation. And we're assuming that that deformation, that property, that relationship between the stress applied and how much deformation occurs is constant throughout Earth's crust of these fault interfaces that we're modeling. Another way to put that is that we're assuming a constant modulus for that elasticity. Again, modulus is a word that we'll use very often in engineering and materials science, but that is just the parameter or the coefficient that relates the amount of stress applied to a specific material and the deformation that will occur from that. Think of how, again, the modulus of a piece of metal, a specific type of metal, is going to be much higher than it is for like silly putty or Play-Doh or some kind of soft material that I just push on it with a little bit of force and it deforms a lot. Others have a higher modulus, that is to say, it takes more force to create that same amount of deformation. We're also going to assume that in the region that we're dealing with, that Earth's surface is flat there. That again just simplifies our calculations of that deformation. And overall, these are good assumptions due to the fact that our region of interest that we're modeling is very, very small compared to Earth's radius in general. And because this rupture is just such a small portion of the entire globe, we can also be confident in our assumption that this is a uniformly elastic material. Here's just a kind of another way to look at that, specifically in the case of earthquakes. So we have kind of this pre-stressed state where this fault interface is just, it doesn't have any pressure on it at all. But eventually the rock becomes stressed and we get some deformation. They start pushing past each other and that builds up a lot of stress. And eventually we have a rupture on that fault that happens separately. In our case, in this Okada model, we're saying it happens instantaneously. And then we kind of get this, this new deformation after that rupture. This is a really good visualization of what our model is doing. We're taking these geometries, these angles, we're saying, hey, based off of this, based off of the elasticity of the Earth, how much deformation, how much movement of the Earth's crust, as you can kind of see here, how much movement of the Earth's crust are we going to get on this side? If you kind of think of this as flipped, 90 degrees, if we have these two faults here that are building up pressure, kind of at that interface there, and eventually they slip, we're going to get one of them is going to get pushed higher than the other. And that kind of upward deformation, or also the downward deformation on the other, is what creates that rapid change of the ocean seafloor that generates the tsunami wave. So hopefully you can see how these things are all coming together. So another thing that we're going to do with this model is we're going to allow our rupture zone to be split up in order to follow the fault's curvature. And I'll show you what we mean by that. Because most faults are not perfectly straight. If they were, we could model it just as a single kind of rectangle of, hey, we have a rupture zone of this length, this width, it's at this angle, and we want to model what happens to the ocean seafloor when it slips this much, or when we get this much deformation from that rupture. But especially in several of the tsunamis that we've modeled, the actual fault interface is curved. And so with that, we have to do something called subfault splitting. And kind of the technique that we'll use for that, we'll return to this when we look in the code, because we have some specific functions that are going to allow us to do this, is we choose our epicenter point, which we will just kind of put right there. And then we also lay down points along the length of the rupture zone that we want to model. And then we also lay them along the width. So this way we get kind of this bent rectangle that is following the curvature and geometry of that fault. And with that, we get a bunch of these little rectangles that when put together, kind of sum that rupture zone. I think another excellent way to visualize this is to go, we'll go now quickly to the source, the documentation for Geoclaw. And we'll look at this because this gives us some really interesting information. So in this introduction here, they're kind of recapping a lot of what we say, that we're making these assumptions, we're using these elastic properties of the Earth. I'll include these links for you to read through if you'd like. But essentially what they're showing here is that yes, we can model kind of these little rectangles of a fault, and we can give it that rectangle, we'll define it by the Okada parameters, that latitude, longitude, strike, slip, dip, rake. Maybe I'm forgetting one or two of them, but I think you get the idea there. So we see that when we have this guy here, this is kind of a top view looking down at that rectangle. If we were to look from the side profile, we get something that looks like this, showing kind of the angle that is going at. We also get the depth at which that fault interface is at. And what's really, really cool about this is that this also has a nice animation of the deformation that occurs here. So you can kind of see that with this rectangle, we can model, hey, with this direction, and if we apply this slip, we're going to get positive deformation here and negative deformation on this side. So that is to say that now the fault has displaced. You can kind of see that bottom right here, so that this chunk of Earth is pushed up, this chunk of Earth is pushed down, which is going to generate our tsunami wave once again. And they have some really cool simulations here. For example, what happens to that deformation zone as we vary the strike. And so let's look at this to see it. You see that as you change that strike or the orientation of that rectangle, you get different deformation paths with those, if you fix all the other parameters that are there. So that, I think, is a really cool way to kind of build some intuition for how these parameters affect what the deformation looks like. This one here, we are varying the dip. That is to say, the angle, you'll see down here in this bottom left, the angle that that fault is at. And notice how those deformation points change of which side the deformation is occurring on. And again, notice that this rectangle is just kind of this bird's eye view here. So as that dip angle increases, we get a skinnier and skinnier thing. As we vary the rake, again, this is to say kind of the angle that those two fault interfaces are coming against each other. We see that we get deformation that's changing orientation relative to that fault interface there. And maybe the last one we'll look at here is varying the depth. You'll see on the bottom right here, just as we go deeper and deeper, that also changes kind of the the nature of how that seafloor deforms, which is also quite interesting. So the great thing is that Geoclaw has a lot of this functionality already built into itself. We'll also take a look at now this other documentation page, which I'll also attach, which is showing kind of how we're splitting up those rectangles as we follow the curvature of the fault. So notice here that instead of having one big long rectangle that describes the entirety of the fault, we split up into several different, so we can kind of approximate with more and more rectangles the actual geometry and the actual characteristics of that rupture zone. So look at here, now we can have rectangles with varying amounts of slip as we go along that length. So this one here, they give an example of a fault off the coast of North America here near Alaska, and showing that when we split that up, we can also now model more complex geometries in that deformation. And last but not least, essentially the way that we're going to model this, the way that Geoclaw does it, is we do all these computations based off of this rupture zone of how that seafloor is going to change. So we're going to get some parts that are going to be pushed up, some parts of the seafloor that are going to be pushed down. And essentially what we do is now we add those changes to the existing bathymetry or the existing seafloor elevation, as you can kind of see here. So we'll just kind of start out with our original initial seafloor topography or bathymetry, and then we'll add that deformation to that existing thing. And with that, that's how we'll generate that wave. And we'll see later on how Geoclaw now is propagating that wave, how we model that, how we capture what that simulation looks like through the region, through the various islands and coastlines that wave is going to pass through. So overall, this has kind of been our summary of these geological terms, how we're going to use those to model and describe these earthquake ruptures. And just all this terminology, I hope is going to be more clear, because as we go into the code, we're going to see a lot of it, again, these different terms, this Okada model. So I will continue to attach a couple links for further reading if you're interested, and we'll see you in our next video.